Hello everybody and welcome to exercise part B of exercise 2. We are looking at page 39 here in the workbook. And let's read this question together. So for each of the following, find permutations of each of the specified orders in the group if possible. And if it's not possible, then show why not. We want to give a brief proof. Okay, and in this video we're just going to look at part B here. So they'd like us to find elements of order 6, 12, and 15, if it's possible, in the group S7. We might start by reminding ourselves what that group S7 really is. Okay, it's just the set of all permutations, okay, sets, functions that are one-to-one and onto, of the set of the first 7 positive integers. Okay, and just a little tip here. So when you're asked to find elements of a particular order in a permutation group, generally the best type of element to try for is either a cycle or a product of disjoint cycles. Those are the easiest types of elements to find the orders of. All right, so let's start with order 6. Can we find an element of order 6 in S7? Okay, well, the easiest way to do that is just to take a 6 cycle. Okay, so how about the permutation that takes 1 to 2 to 3 to 4 and so on, up to 6 and then back again? Is that a valid permutation in S7? It definitely is, because in S7 our available set of elements looks like numbers between 1 and 7. We've only used numbers between 1 and 7. The fact that 7 is not used just indicates that this permutation leaves 7 fixed. Okay, and the fact that this is a 6 cycle tells us that the order is 6. Okay, so there's an element of order 6 in S7. We're done with the first number. What about 12? Is it possible to find an element of order 12 in S7? Okay, well, you might initially be skeptical of that because 12 is a number that's bigger than 7. We only have 7 numbers available. Okay, so we can't get an element of order 12 by taking a 12 cycle. We don't have enough numbers in the set that we're permuting. Okay, but could we get 12, an order 12 element as a product of cycles somehow? Okay, well, remember that if you take a product of disjoint cycles, you can get the order of an element like that by taking the least common multiple of the cycle lengths. And we can get 12 by taking the least common multiple of 4 and 3. And so a way to get an element of order 12 would be just to take a 4 cycle and compose it with a disjoint 3 cycle. Okay, notice that that is a legal permutation because we've only used the numbers in the set 1 through 7, and it's a disjoint product of cycles, so its order is going to have to be the least common multiple of the product of, or the least common multiple of the cycle lengths. Okay, so this has order 12, which is LCM of 4 and 3. Okay, so the answer to the first two parts of this question were yes, we were able to find elements of order 6 and 12. Now, what about 15? Can we find an element of order 15 in S7? Okay, well, if you think about this, ask yourself, how might we get a number 15 for an order? One possibility would be a 15 cycle. We know that we can't do that because we've only got 7 numbers in our set. Okay, so the only other possibility is to maybe get 15 as the least common multiple of a product. Okay, and what comes to mind for me is the least common multiple of 3 and 5. That's a possibility, but does that work in this set? If we had a cycle of length 3 and another disjoint cycle of length 5, 3 plus 5 is 8. That's more elements than we have in our set. Okay, so I'm not feeling optimistic about this. It doesn't look like we can get an element of order 15. So let's see if we can prove that it's not possible to get an element of order 15. Right? We're going to do a little proof by contradiction here. So we claim that S7 has no element of order 15. Okay, for suppose, by way of contradiction, I'm going to abbreviate that BWOC. That just means by way of contradiction. Okay, that there were such an element. We'll call it beta. Okay, so we're assuming by way of contradiction that beta is an element of order 15. Well, if such an element exists, then we can decompose it into disjoint cycles. Okay, so we'll assume that we have such a decomposition. Now, the only thing is, we don't know how many cycles there might be, so we kind of have to think arbitrarily here. So let's suppose that the lengths of the cycles are k1, k2, up to kn. We don't know how many there are, so we'll just assume that there are n of those disjoint cycles. Okay, now let's see what has to happen here. Okay, well, one thing that has to be true is that the sum of all these cycle lengths can't be bigger than 7 because of the fact that we only have 7 elements in the set that we're permuting. Okay, so if these cycles are really disjoint, then the sum of all of their lengths can't be bigger than 7. Okay, so just to give you kind of a brief words to go with this, this comes from the fact that we have only 7 numbers to permute. Okay, so that's one thing that would have to be true here. Okay, the other thing that has to be true, we assume that beta has order 15, so the least common multiple of all of these k's okay, sorry about my writing here. That has to be 15. All right, but let's think about what the possibilities are. What would have to happen in order to get a least common multiple of 15? I can really only think of 2 possibilities. Okay, one possibility is that one of the k's might be a 15. Okay, that's certainly possible. Okay, and the only other possibility I can think of is that maybe 3 divides one of the k's and 5 divides another one. If you think about it, those are really the only possible ways that this could happen. Let's write that down. So the only way to obtain this and let me be a little bit more specific, to obtain this least common multiple okay, is if 15 is a divisor of one of the ki's. Okay, remember that notation, 15 divides into ki for some I, or 3 divides ki and 5 divides kj. Okay, for some I not equal to j. That second part of the sentence just says that there's got to be one of the k's has a factor of 3 and the other one has a factor of 5. That would be another way we could get a least common multiple of 15. Okay, but think about both of those possibilities one at a time. If 15 divides ki, that means that one of the numbers over here on the left has to have 15 as a factor. That's going to give us a number on the left-hand side that's at least 15. That's a false statement. 15 is not less than or equal to 7. Okay, so that can't happen. The other possibility is that 3 divides into one of the ki's, 5 divides into one of the kj's. That means that one of these numbers is at least 3, and another one is at least 5, but 5 plus 3 is 8. That's bigger than 7. That's also not true. So what we notice is that both of the possibilities here lead to a violation of equation star, and that's a contradiction. Okay, so let's write that down. Okay, which is a contradiction. Okay, and that contradiction indicates that we can't have an element of order 15 in this group. Okay, and we're done.